stochastic gravitational wave background from the cosmos.
I'm Chang. I'm from UCU side. Then this work is collaborated with my advisor, Yang. So today I'm planning to introduce the formation of a cosmic string and physics of it, instead of present some detail of calculations. So recent years, we have some detectors. It's going to detect the gravitational wave. It's a stochastic gravitational wave. So for example, like IPTA or SKA or LISA or LIGO. And recently we have a constraint from LIGO, for example, the second data release. This is a strong constraint, and this IPTA is also another strong constraint for any new physics from early universe, which can contribute to the gravitational wave. Okay, the example, how does the cosmic string to be formed in the early universe? One of easier example is like a boat. If you have a boat, it's like a universe. Then when the universe is going to cooling, going to expanding, going to diluting, the water in the boat will going down. Then eventually you will see the ground for the boat. Then the ground for the boat is like this vacuum, the vacuum structure of the universe. So if you do the calculation like Fourier transform, you will find the particle, the field in the ground state cannot enter into this mountain. So this mountain will give you like the ground, like a boundary. The particle cannot enter into this string. Then you can, on the other hand, you can go to do the calculation for the. Yes, if you want to do the calculation, it's a very simple. Just going to solve the equation of motion. Then you will find the solution is like space. It's like it's a phase symmetry. I mean sphere symmetry. Then you have a radius dependent function. Then you will find this field. You will find the probability to find at the string is 0, but the probability to find this field is 1 on this far away from the string. So on the other hand, you can do the calculation to find the energy for a string. For dimension 4, you will find, okay, there is the energy density on the right, the position of a string. Okay, but not all of the potential, not all of the vacuum structure can provide the string. Only if the vacuum of the manifold for your vacuum of manifold is not simply condensed. That's why you can have a topological string. So that's a review. So today, listen. This is the simulation for a string evolution. Okay, initially. Let me just going to show you the video. Okay. Okay, this is the time when the symmetry just break. So the string just get formed. Then this small box is your Hubble box, so it's your universe. So some of the string will go into your universe, but some string will just dilute or decay. Okay. Then eventually they will decay to gravitational wave or some ghost particle, depends on your model. So if you're going to do the equation of motion for string, this looks like this ugly function. But anyway, the first term is like dilution from the expansion of the universe. But the second term is like fraction, because you have an interaction between the string and your particles in the universe. But the third term is like the chop rate, because the string will chop to the loop, then loop will surely dilute, will surely decay to the gravitational wave or some Asian or coastal, depends on your model. Okay. Then the fourth term is gravitational wave. The long string will decay to a gravitational wave, but this term is obviously is suppressed by the Hubble mass, the Planck mass. Then another term is the string will straightly decay to the ghostal. Okay, obviously this term is very small because you have a Hubble. This term is also small because the velocity squared, and also you have some fraction. And if the temperature of the universe is going to very low, this one will be suppressed. Then this one is suppressed by G. This one is suppressed by velocity to 6. So this the chop rate is dominant in the universe. So the cosmic stream will mainly chop to the loops. The loops will eventually decay to the gravitational wave. Let me show you other videos. Okay, please see. Okay, this is collide between two loops. Then you will surely decay to the particles or gravitational wave, depends on your model. Okay. So if we're going to solve the equation of motion, we will find, okay, the loop, the size of a loop is like a very simple functions. It's like, okay, initially you have a size of loop. Then later on you will decay to a gravitational wave, but also some Gaussian particles. Okay. Then this is our results. My collaborator is not only going to do the global string, but also have a gauge string results. And this related density for a gravitational wave is looks like this. Then for each frequencies, you will find for gauge strings, it looks like, okay, you have a mountain right here, but the mountain will depend on your symmetry breaking scale. Then have a flat line right here. Okay, this is already known for more than 30 years. We understand the gauge string very well. But how about the global string? Previously we only know the global string from gauge string. We have to do some assumption for the global string. The reason is because we are hardly to do a simulation for the global string. The reason is like, okay, for the global string, we are not only care about the size of string, it's 1/hour, but also we care about the width for the string, it's 1/symmetry breaking scale. So these two sizes is much different, so you are not able to do the simulation. So that's why simulation people is hard to find, okay, the GW contribution from the global string. Okay, but on the other hand, in this paper we provide a new coefficient to show you the gravitational wave from the global string. Okay, it's from, yeah, we have some details from the Beer's model. It is from semi-analytic models. It's not from simulation. And you will find, okay, here is a flat, but here is a slope, which depends on the equation of motion of a global string. And also depends on the coupling to the Asia. Okay, or you can say the ghostal. Okay, go back to the searching the gravitational wave from the cosmic string. We find, okay, you need a very high symmetry breaking scale to produce large enough gravitational wave signal. then the SKA and LISA, for example, can detect the signal. Then this one is very sensitive to the symmetry breaking scale. So which means is okay, the symmetry breaking scale has to be larger than 10 to 40. Then the resonant condition from the inflation is your symmetry breaking scale has to be lower than 10 to 60. So you only have a very tiny parameter space can detect the gravitational wave from global stream. This is okay the major difference to cosmic stream. On the other hand, okay, we consider the standard cosmology. How about the non-standard cosmology? Firstly, we consider, okay, at some time you have a phase transition from some non-standard cosmology to the standard cosmology. So for example, this red line. If you have a connection domination in the early universe, then it will translate to standard cosmology at some temperatures. You will find because the connection dilution is weaker. So you will get a stronger signal from the gravitational wave itself, of course. On the other hand, your early universe is dominated by some matter domination. They have a stronger dilution, so you will decrease. So this is another probability to detect a new physics from early universe. Okay. By this detector like or LISA. Okay. On the other hand, for the question, how much earlier we can detect from this global stream? Okay, one we can do like, okay, you get equation of motion, then you do the calculation for loops. You find the loop is time dependent. But the gravitational wave from the loop is also time dependent. But you can replace the time by temperature. So you know which temperature you can get which frequency from the global stream. So that's how we can draw a single line for the global stream. Then also this true line is for gas stream. And for some CMB reasons, the global stream, the highest symmetry breaking is bound by this value. So which means is, okay, for example, from ETCE, the global stream can detect the early universe temperature correspond to 10 to 8 GeV. But from the gas stream, it's only to 10 to 4 GeV. So the global stream are able to detect the universe is much earlier than the gas stream. So it's a good news for us. Okay. So for conclusion, we developed the new analytical progression for GW from global stream, but I didn't show you today. Anyway, another thing is the global stream, the gravitational wave from the global stream is detectable if you have a very high symmetry breaking in the early universe. Okay. And recent detectors are able to discover the new phases in the early universe up to 10 to 8 GeV temperature. So it's a very very new things for cosmology. Okay. On the other hand, how long I have?
5 minutes.
Okay, because today I show you the global stream. Is if you potential is like this. If you only have one mountain in the bottom of the bottle. But if you buy the Coca-Cola, you will see, okay, there have several mountains around the circle, which break the symmetry for this circle, right? Which means is you break the symmetry for Asian. Which means is this potential is Asian potential. So basically, I think probably the Coca-Cola have to pay the money to PQ because they provide this potential for Asian symmetry. Okay, this is funny things. Okay, that's all what I want to say today. Thank you.
Any questions? So you have in Japan the CMB
Yes, very good questions. Let me show you the CMB questions. the CMB constraint is basically is like a triangle like here, if you remember. But the interesting thing is, okay, because the f is function of time, so here this part is early of universe, then this part is later time. So T0, I mean the current universe is right here. Then this part is early universe. So C and B is basically right like here. Then you will find, okay, but the signal from the global string, I mean this signal or this is after the C and B. So we just avoid the constraint from C and B. Okay.
Any question? Let's thank Chia.